So let's order them from longest wavelength to shortest wavelength. And longest wavelength corresponds to lowest frequency, or smallest frequency, and shortest wavelength corresponds to highest frequency. And highest frequency is going to mean highest energy. And lowest frequency corresponds to lowest energy. So what has the longest wavelength, lowest frequency, and lowest energy? So which EM wave or electromagnetic wave has the lowest frequency, lowest energy, or longest wavelength? The radio. What comes next? And we have microwave. Then we'll have infrared. After infrared, we have the visible light. After visible comes what? Ultraviolet. And we can look, if we need to remember how the colors go. Red is going to be on the side with infrared. Violet is going to be over here. So red, orange, yellow, green, blue, indigo, violet. So red is going to be over here. After ultraviolet goes X-rays. And after X-rays goes gamma rays. So if I wanted to compare, let's say, infrared versus blue, which one has a longer wavelength? Which side is it closest to? The longer wavelength or the side? So infrared is closer to being on the longer side. So infrared has a longer wavelength than blue. Which has more energy, microwaves or UV light? So remember, the higher energies is over here. So this side has higher energy, higher frequency, and shorter wavelength. So looking at microwave versus UV, UV is closer to the higher energies. So UV has higher energy than microwaves. Which has a lower frequency, yellow or violet? So yellow is on the left, so we choose the left. So yellow has a lower frequency than violet. That's really all we do to figure out if something is lower or higher. We look if it's to the left of the other thing, it's going to be one of these. So radio versus microwave. Radio is to the left of microwave. So it will fit all these. It has a lower wavelength, a lower frequency, and a lower energy. Have a look at visible light versus X-rays. X-rays is to the right, so we choose these terms. This is because it's to the right of visible. It is a shorter wavelength, a higher frequency, and a higher energy than visible. Visible is to the left, so visible has a longer wavelength, a lower frequency, and a lower energy. The only thing you have to really do is memorize this order. And know that the left side is longer wavelengths, lower frequency, and lower energies. The right side is going to have your shorter wavelengths, your higher frequencies, and your higher energies. So let's talk about some of the properties of light, or electromagnetic waves. If you shine a light on some material, what can light do? Reflect. Properties of EM waves. So one, you can shine a light. So let's say that we have and we're doing this in a completely different order than the other class. So let's suppose that we have a mirror or some surface, some smooth surface. We can have light come in, and it can reflect off. I'm going to show you the law of reflection. So this is the law of reflection. If I were to draw a perpendicular line to this mirror, this line would be called the normal line. So here I have my mirror, my surface, and I draw a dashed line that is at 90 degrees from it, perpendicular. This angle here, I'll label theta I. This is the angle of incidence. And I'll write this word bigger here in a second. And I'll label this one theta R. This would be angle of reflection. This would be your incident ray. This would be your reflected ray. And one of the most to find out what the theta or degrees it'll reflect off, one of the most advanced equations in physics, theta R is simply theta I. This is known as the law of reflection. So the angle, let me write it big, the angle of incidence equals the angle of reflection. And if you haven't ever seen the symbol, it's theta, the Greek letter T, I believe. So we can see the incident light coming in. So if we do a shallower angle, this angle is small, this angle is going to be equal to that angle. So it's going to reflect like this. If we increase this angle, it's going to increase on this side. So angle of incidence equal to angle of reflection. We have some clear, smooth surface. And these two angles are going to be equal. We draw this normal line, which is just perpendicular to the surface, so at a right angle. And this doesn't have to be, you could also draw it like this. So a light coming down here. Again, if this is our mirror, our plane surface, then when the light comes in and hits here, we draw a perpendicular line. This would be your normal. We measure the angle here, and we know that the reflection is going to have the same angle here. Sorry. So, for example, if you shine a light where it's at a 10-degree angle here, it's going to reflect back out at 10 degrees. If you do it at something like 80 degrees, it's going to reflect off that surface at 80 degrees. And this is known as reflection. So, a EM wave can reflect off of some materials. And this tells us how it reflects off. This is the equation for reflection. Now, why can't you see your reflection, and Alan, put on your mask. Why can't you see your reflection if you walk up to the wall? No, it's reflecting light. I can clearly see light reflecting off of it. It's reflecting a lot of light. No, it's doing a lot. Mm-mm. So remember that these two angles will be the same. So if we have a surface and we come in and add several so let me make this bigger. So I come over here to a smooth surface. Here's my normal line. It's going to reflect off like this. Another line comes in. It's parallel to the first. Normal line is going to reflect off. And come over here. Another line's coming. Going to reflect off. And so we see these lines stay parallel. Now, this is normal reflection, or plane reflection, specular. There's a lot of words for this. But then, what would happen if we have a bumpy surface? So light comes in, strikes right here. Again, we draw something that's perpendicular to the point it strikes. So it would bounce off like this. And let's say that it comes in, strikes right here. Again, we have to do it as perpendicular. So the angle right here would be like that. And let's say another one comes in right here. Or let me make it. So doing that, it would come back like that. So it gets scattered. This is known as diffusion, or a diffuse reflection. Diffusion is when light scatters after striking a material. Yes? This doesn't have to be just reflection. For example, wax paper was the example we used in another class. Have you ever seen wax paper, how it was cloudy? So, if you have some wax paper, Hunter, stop repeating what I'm saying. So it comes in, and then it diffuses in some random direction. This is also known as diffusion. So it's a diffuse material. So looking at better drawings than I can do. So here we don't really need to know specular. That's the proper name of it. But if the material is smooth, it'll scatter light back perfectly. So a mirror is smooth. And the reason why you can see your image is entirely because it's smooth. If it was a diffuse reflection, the angles will, the perpendicular line would be all distorted, and it'll scatter in all random directions. And so you wouldn't be able to see a clear image. Again, so diffuse reflecting for rough surfaces. You see that they all come scattered in. Regular refraction, it comes when you have a true surface, or a smooth surface. So diffuse reflection makes it scatter in random directions because it's unsmooth. So we have that light can reflect or bounce off of something. What's another thing light can do when it hits a material? Not where I'm quite looking. Oh, yes. Absorption. So light can be absorbed in a material or by a material. Let's look at normal light we're used to, the only light we can see. So for visible light, objects that appear black absorb all colors of light. And when they absorb it, they heat up. Objects that are white reflect all colors of light. A red object absorbs all colors except for red. It reflects the red colors back to you. So if you had a red object, and the reason it appears red is because when red light hits it, it bounces or reflects back into your eye. However, when green light hits it, it gets absorbed, while red gets reflected. I would like to also add this. So when you have a diffuse material, you might have heard this. It's translucent is another name for it. A translucent material is semi-transparent, meaning light can partially go through it and scatters light in random directions, so it's diffuse. You need me to keep that? So translucent is a semi-transparent material or property. So here would something be translucent. So light passes through it to some degree, but it scatters it in random directions. Yes. Absent white is where it reflects all colors and doesn't absorb any. So there is nothing truly reflective. Some light is always absorbed. So again, it goes. How our eyes work? Our eyes can only see three different types of colors. Or we have cones. That's biology question. But there's no material that's perfectly reflective. NKP, keep your mouth up. So there's always going to be some amount of light that is absorbed. So no, if you had a perfectly white room, it would not continually reflect it. Some light will always be absorbed. There's no such thing as a perfect mirror. What? You need to rethink about that. So light can be absorbed by a material. And another property is, what can EMs also do? EM waves or electromagnetic waves can also pass through materials. Some materials. What do we call that? Transparency. So they can just go through. So you can have some light, shine light through it, it'll bend a little bit, and then go through. So this material will be transparent to that light. The ability for an EM wave to go through a material depends on its wavelength or frequency. So for example, if I had a red glass, so if I had just a red filter or red piece of glass, would red light pass through it? So if red light hits it, if red light passed through it, we wouldn't see red. So if our eye is right here, we're looking at it. If it's red, that means the red has to bounce back. However, we don't see any green, so the green has to go through it. So if it appears red, that means red is reflected. And the green light will pass through it. So it depends on the wavelength and frequency of the light. So, again, it doesn't have to be visible light. It could be infrared. So can light pass through glass? Visible light pass through glass? Yes, it's transparent. Put your mask on, Alan. What about infrared? Can infrared pass through glass? No. So here's a person holding a block of glass, or a pane of glass. So his body, so remember, things around this temperature is emitting infrared rays. So if we had a camera that can detect that infrared ray, we can see that the glass is blocking it. None of the infrared rays are able to pass through it. a safety precaution if you ever get into lasers. How cheap lasers work is they actually produce infrared, and they then convert infrared by increasing its frequency into visible light. Some of them are not truly efficient, so if you have some safety glasses that block the green light, some of the infrared that's not converted can escape through and damage your eyes. So it's good to test your safety goggles. This is a piece of paper that reacts to or fluoresces to infrared. Let you see infrared a little bit. So here's another example. You can see the infrared that's coming off the glass, but you can't see any infrared going through the glass because it's opaque. So transparency or transparent EM wave can pass through. Opaque light is absorbed or reflected. Have y'all seen trash bags? Have y'all seen black trash bags? If you got into a black trash bag, would you be able to see and put your mask on? Would you be able to see through it? If you put it over your head or in front of you, would you be able to see? So here is a picture invisible. Here's the same image in infrared. So the trash bag is opaque for visible light, but it's transparent in infrared. Well, again, whether something is transparent or opaque depends on its wavelength. So notice his glasses. So remember, glass is opaque in infrared, so we can't see through it. But the plastic is transparent in infrared, so we can see through it. There was actually some people who chose clothing that is completely transparent in infrared. And if your cell phone had an infrared sensor, or you had an infrared camera, and you took a picture of the people, it would appear as if they had no clothes on. Make what? The clothes? I mean, like, it's just an infrared camera. So, the camera, if y'all bring a trash bag, the camera at the doorway when you walk in and measures body temperature, that is an infrared camera. So if you had, well, I think almost any plastic would do it. Even a sandwich bag. It means if you put your hand in a sandwich bag, and but here's the deal, very see-through plastic. I guess you need something black so that you can't see through it, invisible. But that's an excellent use. There was one image. I want to show to you. So, ceramic coffee mug versus a glass. The glass appears black because it absorbs all the infrared and doesn't reflect any or allow it to go back. Oh yeah, if it's plastic. It depends on what type of plastic it is. Yep. Hmm. That's another use for infrared. So let's see what I'm missing. Oh, polarized. So another property of light is polarization. Do y'all know what polarization is? So what type of wave is an EM wave? What type of wave is an electromagnetic wave? This is your previous test, the second question on it. Transverse wave. That means it's shaped like this. And this is in the real world. So when we say it vibrates up and down, so an EM wave, an electromagnetic wave, is a transverse wave where the vibrations are in the electric and magnetic fields. So these electric fields, and I'm just looking at electric right now, these electric fields are vibrating up and down. Well, what if you turn the light sideways so they can vibrate? Stop, Hunter. They can also vibrate in the horizontal direction. They can vibrate in this direction. They can vibrate in this direction. Polarized light polarized light is when all the light is vibrating the fields in the same direction. Have y'all ever used? Have y'all ever had some uh, sunglasses that block polarized light and looked at water? Yes. Can you see into the water better? Yes. So the sun produces unpolarized light. That means it can be in any single direction. And if we had a body of water and it strikes the surface, more than likely the reflected light is going to be all in one direction. And I think it's going to be horizontal. Polarized light will will be reflected. while the rest of the light will go down through, so it'll pass through the water. And so let's say that we have some light that is vertically, so it's done like this. And let's say that we have some polarized filter, where we have lines horizontal. Only horizontal light could go through it. Whereas things that are oscillating vertically would end up hitting. So you can have light that's oriented in any way, but you can come up with a filter, and y'all stop humming. And only light that is vertically polarized could go through. So light, again, can be at any angle, but we can have a polarizing filter that blocks light, and so that they can only go in one way. So depending on the filter, it can block in any way. So a vertical filter would block the light. Horizontal light would only let horizontal through. This is actually quantized to really explain this unique quantum mechanics. But just know that that's how light behaves. So let's see, polarized lake light. See if I can find that image. So yeah, it's going in anyway. Here we go. So the image on the left was taken without polarized filter. The image on the right is after you applied a polarized filter blocking out horizontal light, or blocking out all, horizontal. Because the light that would be reflected is more horizontal. Here you go. So here again, on the left, it's capturing mostly. So the light being reflected off is mostly horizontally oriented light. So if you filter that polarized light off, you would be able to see through.